Hi folks, you can begin by checking your answers to last night's homework. Our warm-up today is going to begin with number 69, which was the Witch of Agnesy. Such an interesting name. I attached the link for you on Google Classroom so you could see some of the history behind this curve. It was studied by Maria Agnesy in 1748, and she wrote a book about it, but it was translated incorrectly. It was originally called the versed sine curve, which was the word avicera, and it got translated into, with two V's, that means witch or wife of the devil. So it's got an interesting name basically because it was mistranslated. But as you go around, if you look at the link, as you go around a circle, if you graph that secant line, you end up generating this curve, which kind of looks a little bit like the bell curve. I guess I have a rough drawing of it here. And this is considered an improper integral because we have two infinite limits at the end. So let's go ahead and work it out. We're going to go ahead and split that up into its two parts. Remember, you can pick any number. So we typically like to pick 0 just because it's very nice to plug in for your fundamental theorem of calculus. So we're going to go ahead and split it up using the 0 into the two parts. And even though this does create two different limits, we have the limit as my lower limit. A goes to negative infinity for the integral from a to 0 for 1 over x squared plus 1 dx. Plus this right here is my upper limit. Limit as b goes to infinity from 0 to b, 1 over x squared plus 1 dx. What's nice about this is that they have the same antiderivative. So when you do this, u sub does not work because if that's your u, the du would be 2x. So this one here is best as a u being an x squared, or as an x, the du being 1 dx, and your a value being 1. This is better as an arctan. So this is going to be 1 over a, so 1 over 1 arctan of u over a, which is going to be x over 1. And this will be going from a to 0, limit as a goes to negative infinity. Just watch your notation here. It can be rather challenging to have to copy everything out to make sure that everything's in the right spot, but you want to keep your limit here until you actually take the limit. So when we do our fundamental theorem, we usually plug in the 0 first. So we're going to have arctan of 0 minus the arctan of a, and we are going to take the limit as a goes to negative infinity for that. Plus, when we substitute in the b, we're going to have arctan of b minus arctan of 0, and this will be the limit as b goes to infinity for that. Now, thankfully the arctan of 0 is pretty easy to remember because we know that the tangent of 0 is 0, so the arctan of 0 will also be 0. Those are pretty easy to do. Now, keep in mind when you stick a positive infinity in here for b, that tangent goes up to positive infinity at the angle of pi over 2. So this part of the limit here will evaluate as pi over 2, plus if we take a look at the other side here, when does the tangent function go to negative infinity? That will occur at this angle measurement, which is negative pi over 2. So this will be minus my arctan of negative infinity will be negative pi over 2. So when we go ahead and evaluate this, then this double negative will become a positive. A half pi and a half pi will equal 1 whole pi. Now this was really interesting to mathematicians because why in the world would you have a curve that looks like that, and the area underneath this curve is going to end up becoming pi? So this was a really interesting question, why pi is showing up in this curve right here, and it does show up then in statistics and probability where, there is no circle really going on in this problem. So it's kind of an interesting bit of history going on right there. All right, today we are going to be talking about the last part of the lesson, which basically the question that we have or that we want to answer is we want to know, can we tell if an improper integral, how could we tell if it converges or diverges without doing the work? Converges or diverges without evaluation. Is there a way that we could do that? Is there some type of time saver that we could have so that whenever I am taking the AP exam that I could just quickly be able to tell? And the answer to that is going to be numbers 49 and 50 from your textbook. So if you'll go to page 585 and take a look at number 49, they're talking about this basic improper integral going from 1 to infinity for 1 over x to some power. So we're talking about our power functions down here in our denominator. Now we have done this before. We already know from previous examples that if I take the integral from 1 to infinity for 1 over x dx, if I do this one here, we know that this guy here diverges. We've already done a problem like that. But the question is, well, what if I raise it up a power? What if I do 1 over x squared dx? And from our homework, we know that something like that converges. And so if you take a look at the graph of what is going on here, and I'm just going to look at the positive first quadrant here. Let's say this is the function 1 over x, just the positive side here, and we're looking at the integral, the area from 1 out to going out to infinity. So this area underneath the curve, this curve is not coming together close enough with the x-axis to say that it's converging, and that's why when we actually evaluate this guy here, it diverges. However, if you take a look at, let me grab a different color here, if you take a look at this guy here, 1 over x squared, and think about 1 over 1 squared, it's going to meet up pretty much in the same place that 1 over x is going to meet up at. But what happens is when I stick a 2 in, whereas this guy here would be at like 1/2, this guy would be at 1/4, so it would be much smaller. And then if this guy, if I stick a 3 in here, this guy would be at 1/3, this guy would be much smaller. So this is coming down closer, very quickly closer with the x-axis here. And so because this one here, 1 over x squared, is going to converge, 1 over x cubed is going to go even lower, and 1 over x to the 4th will go even lower. So if the p-value is greater than 1, it will converge. This is a nice little time saver, but even more than that, they actually have a formula for it. It will converge to 1 divided by p minus 1. So we can actually not only determine that it converges, but we now even have a formula for the area under the curve for that. However, if I have something with a higher, something like the integral from 1 to infinity of 1 over, let's say we have a square root of x. Square root of x would cause that denominator to not be as high. It would go more like this. So 1 over, I'll have the square root of x, would be something that goes higher than the 1 over x curve. So this guy here is also going to diverge. So if p is less than or equal to 1, so if the power is 1/2, 1/3, 1/4, or equal to 1, or like that one there, it's going to diverge. This happens all the time, and so it's called a theorem. Theorem 8.5 from your book is saying this right here, that if p is greater than 1 for the power from 1 to infinity, that would converge, and if it was less than or equal to 1, it will diverge. This is a nice little shortcut This is in Chapter 9, we will refer to this as the p-test, but it is a very, very nice little shortcut. And so we can kind of look at something. For example, we can look at the integral from 1 to infinity of 1 over x squared, and in the past where we would, work it out, we don't need to now. We know it will converge because the p-value is equal to 2, and that is greater than 1, but we also then know that the area will be 1 over p minus 1, which is going to give me an area of 1 over 1, which is 1. Okay, so it's a nice little time saver and a shortcut. So if I had, for example, if I had the integral of 1 to infinity of 1 over x cubed dx, again, we can say, hey, this is going to converge because the p-value equals 3, which is greater than 1, and the area is going to be 1 over 3 minus 1. The area there will be 1/2. Now, we could, of course, check it. We could check it by actually doing the limit as b goes to infinity for x to negative 3 dx, which is going to give us a x to the negative 2 divided by negative 2, which will be a negative 1 over 2x squared, integrated from, I guess I should write this in here, 1 to b, limit as b goes to infinity. So if I stick my b in here, negative 1 over 2b squared minus the negative 1 over 2 times 1 squared. This right here, double negative, will become a positive, so this will be 1/2. When I take the limit as b goes to infinity down here, when I stick infinity here, this term is going to go to 0, so this will be 0 plus 1/2, which equals 1/2. And that's what we said, right? Yay! It works. So it's a nice little time saver for sure, and it really can help us on the AP exam. In converse, we could also do number 50. Number 50 is kind of like the same problem, but in reverse. So if we were looking at the function, let's say I have this function here is 1 over x, and whereas, 1 over x squared is getting closer and closer and closer on this side here, 1 over x squared. On the far end, between 0 and 1, this curve is getting further away from the y-axis. It's getting closer to the x, but it's getting further away from the y. So on this end, it would be diverging more. Whereas if you looked at the curve 1 over square root of x, whereas it's getting further away from the x-axis, it is getting closer to the y-axis on this end. So it pretty much is the reverse of what was happening in that way. So if we have the integral from 0 to 1, where 0 is an undefined point for all of these, for 1 over x to the p dx. So this is still an improper integral because of the discontinuity at the endpoint. If we're looking between 0 and 1, if the power is higher or equal to 1, it's going to diverge, and if the power is less than 1, it converges. So this is kind of the opposite of what occurred in number 50, but again, it's a nice time saver because we could see that. The last thing that could really be a nice time saver for us is not so much if it exactly equals, but if we could guess if it's close enough. So for example, 1 to infinity of 1 over 1 plus x squared dx. We were looking at this curve earlier, right? This is very similar to the integral 1 to infinity of 1 over x squared dx. So we know, according to our time saver, that this guy right here is going to converge because the power is 2, which is higher than 1, and so that one ends up converging. this is so similar. So if I plugged in a 1, this will be a 1, this would be a 1/2, it would be lower. If I plugged in a 2, this would be a 1/4, this would be a 1/5, which is lower. This right here, if I plug in a 3, that's a 1/9, this is a 1/10, which is lower. So even though this curve here is converging, it's really, really close to the x-axis, this one here is going to be smaller the entire way. So if we know that this guy here converges by our theorem, we are going to do a comparison between the two, and almost thinking about it as a limit as x goes to infinity, almost thinking about it as a L'Hopital's rule, comparing one function to another. When we do L'Hopital's rule, we kind of do that. We are going to see, if we look at these two and we look at the comparison and it does go to some limit, then we can say that the improper integral for f of x, the area under that curve, and the integral under the other function both converge, or diverge. So they have to be doing the same thing if that limit between those two exists. And so if we get it close to something that we know, we can also kind of do a comparison and say, hey, you know, this limit here is converging, and this one is really similar to it, so therefore it will converge as well. And so we're going to try to do that on the following problems. We're going to be on page 586. I'd like you to include the ones that we just did, 49 and 50, and then I want you to try using that for 53 to 61 odd. We will take all questions tomorrow and take a look at some special cases on Friday and really prepare for our test next week.